Chapter 3, Lipofuscin, the origin of the autofluorescence signal, page number 27. The retinal pigment epithelium digests the tip of the outer segment of the photoreceptors, which are phagocytosed on a daily basis. The digestion process of these materials, which contain polysaturated fatty acids and byproducts of visual cycle, is overall very efficient, but a tiny fraction is chemically incompatible for degradation and accumulates in lysosomes of the retinal pigment epithelium. This undigested fraction is called lipofuscin, LF. Above the age of 70, as much as 20% to 33% of the free cytoplasmic space of the RPE cell may be occupied by lipofuscin granules and melanolipofuscin granules and compound product of LF and melanin. Lipofuscin is a pigment that exhibits a characteristic autofluorescence AF when excited in ultraviolet, UV or blue light. Fluorescence microscopy of the RPE using UV or blue excitation light reveals distinctly bright orange, red or golden yellow granules. This fluorescence also makes it possible to visualize and measure lipofuscin non-invasively, since the absorption spectrum of lipofuscin is monotonic without any distinct spectral signature, and it would be very challenging to measure it by fundus reflectometry. Spectrophotometry and imaging of the fundus autofluorescence. Fundus autofluorescence was initially demonstrated in vivo by vitreous fluorophotometry, which revealed in pre-injection scans a distinct retinal peak whose magnitude increased with age, as would be expected from lipofuscin fluorescence. These observations led to the development of fundus spectrophotometer, designed to measure the excitation and emission spectra of the autofluorescence from small retinal areas 2-degree diameter of the fundus and to allow absolute measurements of the fluorescence. The device incorporated an image intensifier diode array as a detector, beam separation in the pupil and confocal detection to minimize the contribution of autofluorescence from the crystalline lens. This device was used initially to demonstrate that fundus autofluorescence essentially exhibits the characteristics of retinal pigment epithelium lipofuscin. Fundus autofluorescence is about 2 orders of magnitude less intense than the background fluorescence of sodium fluorescein angiogram at the brightest part of the dye transit. As a result, autofluorescence imaging systems with high sensitivity and or image averaging capabilities are required to record the fundus autofluorescence with acceptable signal or noise ratios and safe retinal exposures. Confocal scanning laser ophthalmoscopy (SLO) optimally addressed these requirements, and the first clinical autofluorescence imaging system was introduced at Moorfields in London with an excitation wavelength of 488 nanometer. Subsequent developments using confocal scanning laser ophthalmoscope system. Non-confocal cameras and different excitation wavelengths have further broadened the field of autofluorescence imaging. Retinal distribution of autofluorescence. Autofluorescence images of the fundus shows a central dark area caused by the light absorption by both retinal pigment epithelium, melanin, and macular pigment that strongly absorbs wavelengths shorter than 540 nanometer. The autofluorescence signal is believed to originate posterior to the photoreceptors because it is affected by absorption by the visual pigments when the latter are not fully bleached. Indeed, the parafoveal difference spectrum log in bracket dark adopted autofluorescence bracket complete dash log in bracket light adopted autofluorescence bracket complete comma clearly reveals the spectrum of rhodopsin. Similarly, the autofluorescence is believed to originate anterior to the choriocapillaries because its emission spectrum does not reveal absorption bands of oxyhemoglobin. In contrast, the reflectance spectrum of the fundus shows these absorption bands at 540 and 575 nanometer. These observations are consistent with the notion that the bulk of the autofluorescence emanates from the RPE. Clinical interpretations of autofluorescence images reinforce this conclusion. The autofluorescence emission spectrum in a full thickness macular hole is similar in magnitude and shape to that measured at about 7 degrees eccentricity because the neurosensory retinal tissues are absent in the hole and the retinal pigment epithelium is roughly intact. Conversely, retinal pigment epithelial atrophy causes the autofluorescence emission spectrum from geographic atrophy in age-related macular degeneration (AMD) to be significantly reduced and distorted. Spectral properties of fundus autofluorescence. The emission spectra of fundus autofluorescence are broad and maximal in the 600 to 640 nanometer region of the spectrum, shifting slightly toward longer wavelengths with increasing excitation wavelength. This rate shift occurs for excitations at long wavelength end of the absorption spectrum for some fluorophores in viscous or polar environments. The rate shift in large part explains the variability of emission spectra maxima reported in the literature, with excitation wavelengths ranging from 364 nanometer lamp used in microscopy to 580 nanometer. The emission peak will vary between 590 and 660 nanometer. The excitation spectra have maximum between 490 and 530 nanometer. In contrast to the spectra measured 7 degrees temporal to the fovea, the foveal spectra are attenuated and distorted. This is due in part to the lower amount of lipofuscin in the foveal area and to the absorption of the excitation light by macular pigment. The difference spectrum log in bracket foveal autofluorescence bracket complete dash log in bracket parafoveal autofluorescence bracket complete comma has the shape of the absorption spectrum of macular pigment. Figure 3.1 inset, and this serves as the basis for the two wavelength autofluorescence method to measure macular pigment. Note that the difference spectrum still decreases with increasing wavelength at 550 to 570 nanometer arrow, where macular pigment does not absorb substantially. This is because of the absorption of retinal pigment epithelium melanin, which decreases with wavelength and is larger at the fovea than at the parafovea. In bracket, retinal pigment epithelium melanin is located on the apical side of the retinal pigment epithelial cell. Bracket complete. Influence of crystalline lens absorption. Excitation and emission spectra of fundus autofluorescence are affected by absorption and scattering in the lens and the other ocular media. For example, an excitation at 488 nanometer is attenuated on average by factors of 2.2 and 3.3 for ages 20 and 70 years respectively. The autofluorescence emission is also attenuated, but to a lesser extent, because it occurs at a longer wavelengths, factors 1.4 and 1.5 respectively, when averaged over emissions from 500 to 700 nanometer. If absolute autofluorescence levels are needed, then corrections to account for the excitation and emission losses are required. These losses can be estimated for each subject by psychophysical or reflectometric methods. Alternatively, algorithms that predict the average light loss at a given wavelength and age can be used in population studies. Corrections obtained with such algorithms result in a marked increase in autofluorescence. The corrected excitation spectrum is shifted toward shorter wavelengths where lens absorption is highest, but the shape of the emission spectrum does not change substantially. Now, figure 3.1. Fluorescence spectra measured in a 52-year-old normal subject at 7 degrees temporal to the fovea 7 degrees T and at the fovea sampling area 2 degrees in a diameter. Continuous lines, emission spectra in bracket excitation wavelength as indicated bracket complete, line with field triangle, excitation spectrum for emission at 620 nanometer. The excitation spectrum is not measured but is constructed from the fluorescence at 620 nanometer and plotted against The excitation wavelength dotted line, the foveal spectra are lower than at 7 degrees temporal, particularly for excitation wavelength shorter than 490 nanometer, where absorption of the excitation light by macular pigment is revealed. Insert different spectrum in bracket log bracket foveal autofluorescence bracket complete minus log in bracket parafoveal autofluorescence bracket complete. Converted to macular pigment density using the absorption coefficients of the macular pigment. Age and fundus autofluorescence. Fundus autofluorescence has been shown to increase significantly with age, confirming data obtained in ex vivo studies. The rate and time course of this increase varies among different studies, probably as a result of difference in population selection, techniques, correction method for media absorption, and other factors. The increase of fundus autofluorescence with age for a population of normal subjects shows a large but constant variability. In bracket, the coefficient of variation per decade of age is about 25 and 28%. Foveal autofluorescence increases similarly with age, however, the ratio of the autofluorescence at the fovea to that at 7 degrees temporal to the fovea does not vary with age. We observed a decrease in autofluorescence in subjects above the age of 70, contrary to other studies that demonstrated a continuous increase in autofluorescence above age 70. Albeit, with decreasing rate of increase, the decrease in autofluorescence at ages higher than 70 years could result in part from an undercorrection by our media optical density estimates or from changes in autofluorescence deficiency. Figure 3.2 normalized lipofuscin excitation spectra measured at 620 nanometer, bold phase letters, and emission spectra for 470 nanometer excitation light phase letters. The pairs of spectra are A. Spectra from the 52-year-old subject of figure 3.1, 7 degrees, not corrected for ocular media absorption. B. The same as A, but corrected for media absorption. The autofluorescence at 620 nanometer was 4.2 times larger than for A. C. Ex vivo spectra measured in the RPE of a donor eye, age 83 years. Figure D. Spectra measured on a large druce in a 70-year-old ARM patient, and E. Spectra measured in the same patient in an area devoid of visible drusen. Spectra B, D, and E were corrected for media absorption using the algorithm Van de Kratz and Van Noren. Figure 3.3 Age-related changes in fundus autofluorescence for subjects with normal retinal status. The excitation wavelength was 550 nanometer and the fluorescence was measured in the 610-630 nanometer spectral range. 610 to 630 nanometer spectral range. The data were corrected to account for absorption by the ocular medium. Retinal pigment epithelium fluorophores. Emission spectra measured in vivo are consistent with those obtained in ex vivo measurements on donor RPE and individual lipofuscin granules. The emission spectra in vivo correspond with that of the most efficient fluorophore, fluorophore 8 and fluorophore 8 of several identified by Eldred and Katz from chloroform or methanol extracts of human RPE. Fluorophore 8 was later identified as a bis-retinoid called A2E. Fluorophore 8, other name bis-retinoid, also called as A2E, and is the most extensively studied lipofuscin component. What is the most extensively studied lipofuscin component is fluorophore 8, also known as bis-retinoid or A2E. The photophysical and harmful properties of A2E were recently expertly reviewed by Sparrow. The excitation spectrum in vivo corresponds well with ex vivo measured excitation spectra from donor RPE. However, the in vivo excitation spectra correspond only roughly with those obtained from lipofuscin granules and are substantially broader than the absorption and excitation spectra for A2E in solution. The latter are maximal at 440 nanometer and their spectral width is about half that of in vivo excitation spectra. This implies that A2E is only one of the lipofuscin fluorophores responsible for fundus autofluorescence. Other byproducts of the visual cycle, such as the ATR dimer, could account for the observed differences. RPE melanin, particularly in its oxidized form, also exhibits fundus autofluorescence when excited in the near infrared. Because the absorption spectrum of melanin is very broad, it is possible that RPE melanin contributes to the autofluorescence measured with short wavelength excitations. The contribution of the autofluorescence of RPE melanin to the total autofluorescence for short wavelength excitation is still not known. It was estimated to be 3% to 10% from the absorption spectrum of melanin and 5 to 25% to 25% from ex vivo experiments on lipofuscin and melanin granules. Melanolipofuscin is increasingly present in the aging RPE cell, and it is likely that it contributes the autofluorescence signal. Doshio et al. Showed that melanolipofuscin has a fluorescence efficiency intermediate between those of melanin and lipofuscin, and that its emission spectrum was blue shifted composed to that of RPE lipofuscin. Autofluorescence and Brooks membrane deposits. Evidence of a substantial secondary contribution to the fundus autofluorescence signal comes from changes in the shape of the emission spectra observed with age and disease. Indeed, the three emission spectra in figure 3.2, spectra B, E, and D, are increasingly shifted toward shorter wavelengths as age and the expected amount of Brooks membrane deposits, BMD or drusen, at the measurement site increase. This blue shift is best characterized by the wavelength of maximum emission or the ratio emission at 560 nanometer or emission at 660 nanometer. At 7 degrees temporal to the fovea, the emission peak wavelength decreases and the ratio increases with age, indicating that the blue shift is more substantial in older patients. Furthermore, the blue shift is also more pronounced for spectra measured in age-related maculopathy, ARM patients. Although an increase in the amount of melanolipofuscin could contribute to this shift, see above, the magnitude of the changes and the additional blue shift at the site of drusen suggests that BMT are responsible for this shift. This confirms ex vivo measurements indicating that the emission from Brooks membrane and BMT is similarly blue shifted compared to the emission spectrum of lipofuscin. Spectral analysis predicted the BMT emission spectrum to be somewhat narrower than the LF emission and to have a maximum around 540 nanometer. Spectral deconvolution of spectra from ARM patient showed that the autofluorescence excitation 488 nanometer from BMD contributed on average 20% range 5% to 45% of the total autofluorescence detected between 500 and 700 nanometer. This autofluorescence could play a role in varying appearance of drusen in autofluorescence images in ARM patients, age-related maculopathy. The unique autofluorescence of drusen is also demonstrated by ratio imaging using pairs of autofluorescence images obtained with different excitation and emission bands. As shown in figure 3.5, one image was obtained using bands similar to those used in routine autofluorescence imaging, whereas the other was obtained with excitation at 550 nanometer. The ratio image thus reflects the difference in the local excitation spectra for both the macular pigment and the drusen. The latter are seen in the ratio image as uniform areas corresponding to their location in the monochromatic image. Differences in the excitation spectra of drusen and their neighboring area are thought to be responsible for this effect. Other secondary fluorophores. The blue shift at the fovea in the youngest subjects, figure 3.4, decade 3 and 4, compared with decade 5, must be related to other secondary fluorophores. The autofluorescence from lipofuscin at the fovea in young subjects is very low. Therefore, secondary fluorophores emitting in the 500 to 540 nanometer spectral range may become relatively more important. This fluorescence is believed to originate anterior to the macular pigment and could be from the macular pigment itself, from flavins in the inner retina, from collagen and hyaluronic acid in the vitreous, and from Lane's lipofuscin reflected by the fundus. Autofluorescence from microglia in the inner retina of normal mice has been observed by autofluorescence imaging in some, but not all studies. When seen, the autofluorescence emission of microglia appears to have lipofuscin-like characteristics, although determination of the excitation spectrum would be required for comparison with RPE lipofuscin. However, autofluorescence of microglia has not been observed in normal human eyes by autofluorescence imaging. If the density and autofluorescence characteristics of microglia in normal human and mice were similar, then their observation in mice but not in humans might be explained by a lower autofluorescence emanating from the mice RPE than from the human RPE, causing their contrast to be high enough to be observed. This could result from a lower amount of RPE-LF in mice and from a higher density of RPE melanin, larger attenuation of the autofluorescence of RPE lipofuscin in AF images. Finally, AF autofluorescence contributions from the choroid and sclera have been estimated in age-related macular degeneration patients, age ranging from 69 to 81 years old, with geographic atrophy to be 6% to 15% of the total fundus autofluorescence for dark and light pigmented subjects, respectively. This suggests that choroidal melanin absorption modulates the autofluorescence from other choroidal fluorophores. The contribution of choroidal autofluorescence to total fundus autofluorescence will be less in younger subjects because of the higher concentrations and absorption by melanin in the RPE and choroid. Emission spectra measured in geographic atrophy give little information about the origin of the weak autofluorescence because of distortion by blood absorption and noise in the spectral data. Endogenous fluorophores in the choroid may include stromal elastin and collagen, porphyrins, melanocytic melanofusin, and macrophages containing blue-emitting lipofuscin. Topographical distribution. Ex vivo studies have shown that the amount of RPE lipofuscin is low at the fovea, increases gradually to a maximum about 10 degrees from the fovea and then decreases toward the periphery. Topographical distribution of fundus autofluorescence measured with an excitation at 550 nanometer and thus not affected by macular pigment absorption confirms these findings. The autofluorescence is maximal at an eccentricity of 7 to 13 degrees, where the autofluorescence is about 1.7 times higher than at fovea. The central minimum is caused principally by lipofuscin in the retinal pigment epithelium. Since the higher concentration of retinal pigment epithelium melanin at the fovea has been estimated to be only 1.15 higher than at the parafovea, fundus autofluorescence is not symmetrically distributed around the fovea. The autofluorescence is maximal at about 12 degrees temporally and superiorly, lower inferiorly, and nasally, where it is maximal at about 7 to 8 degrees from the fovea. The autofluorescence distribution roughly matches the distribution of rod photoreceptors, which is not surprising given that lipofuscin derives from precursors within the phagocytosed photoreceptors outer segments. However, the distribution does not reflect the narrow distribution of cones at the fovea. The rate of lipofuscin formation from cones may be slower, as suggested by the observation in rhesus monkeys that the number of foveal cone-derived phagosomes in the retinal pigment epithelium was only one-third that of extrafoveal rod-derived phagosomes. Other effects such as high absorption of retinal pigment epithelium melanin and fovea, cone or rod differences in the fractional content of indigestible materials in the phagosomes, and spatially dependent protection by the macular pigment could also play a role in reducing foveal lipofuscin formation. Summary: the fundus lipofuscin signal derives principally from retinal pigment epithelium lipofuscin, as evidenced by its partial distribution, its spectral characteristics, and its relation to age. This signal is affected by absorption by the ocular media, macular pigment, retinal blood vessels and capillaries, and RPE melanin. Secondary sources of lipofuscin in humans are BMT and vitreous fluorescence. The autofluorescence of drusen may provide specific information about the type of content of drusen. A case can be made for using excitation wavelengths longer than the 488 nanometer currently used in most fundus autofluorescence imaging systems. Indeed, there would be less ocular media absorption and scattering, and errors associated with correction for media absorption would be decreased. Macular pigment absorption would be reduced, if not eliminated, allowing for clear visualization of the foveal RPE. One would also expect an overall increase in the signal intensity and signal or noise ratio. Finally, longer wavelengths are less susceptible to photochemical damage to the retina. Figure 3.4. Age-related changes in the shape of the emission spectrum, excitation 470 nanometer, as characterized by the maximum wavelength top and the ratio of the autofluorescence at 560 nanometer to that at 660 nanometer bottom, open circles, normal subjects, field circles, patient with ARM, age-related maculopathy. The spectra were corrected. The spectra were corrected to account for absorption of the ocular medium. A decrease in the dark wavelength and an increase in the ratio results in the blue shift of the emission spectra. Figure 3.5. Lipofuscin images AB and a 550 nanometer monochromatic image C from a 65-year-old ARM, age-related maculopathy patient. Figure A, obtained with excitation at 470 nanometer and a detection more than 510 nanometer. And figure B, obtained with an excitation at 550 nanometer and a detection at more than 600 nanometer. Then D, the ratio after alignment of A to B, all images were recorded with a non-confocal camera. Note that the attenuation by the macular pigment seen in A is not seen in B, allowing examination of the foveal RPE. Figure 3.6, topographical distribution of fundus autofluorescence based on measurements along the horizontal (nasal temporal (NT) and vertical superior inferior (SI) meridians. The autofluorescence is expressed relative to that at the fovea. So here we conclude the chapter 3. Good night.